My name is Tony Rivera. I am the director of LUCAS. That's the Laboratory for Unconventional Conflict Analysis and Simulation. We're bilocated at Duke University and Fort Bragg, where we do, consultation and tool development for psychological operations and civil affairs. And we are the premier computational security studies lab in the country and in the world, and I can say that because we invented that term. We're hoping you like it and it catches on. Lucas's current work is a Minerva Initiative grant, and this is the grant number. I'm just acknowledging the wonderful support we get from the Army Research Laboratory and the U.S. Army Research Office, Lisa Troyer. I won't mention any names. And to also, the necessary caveat that the views expressed here are my own and not that of the Department of Defense or the U.S. government. And so today I'm going to tell you a little bit about how we at Lucas see the world, how we do some of our research, some of our questions, some of the technology we're developing, and how we develop teams to engage this very interconnectedness in this networked world. So we're going to linger on this slide for a minute. What do wolves and Yellowstone National Park and international security have in common? I mean, at first blush, it may look like not much, right? But when we dig down, there's a possibility that there's some basic science here that can help us inform both, and through that basic science, also engage international security, environmental security, human security, with tremendous implications for STEM and other types of research. To my mind, the answer lies in discovering the underlying complexity. So the wolf story is actually it's really quite fascinating, really. So wolves had become extinct in Yellowstone National Park, and it had tremendous effects, although it wasn't clear until they were reintroduced by a team of scientists. They soon found that the elk population, which had been overgrazing, causing degradation of the environment, had to move to avoid the wolves. That allowed for reforestation. Trees were coming back where they hadn't been seen in years. Other types of vegetation. This brought in birds. Soon the river banks were solidified. Beavers come back into the arena. So what's happening here is by the introduction of wolves, the entire landscape changes and becomes more stable and more welcoming to different types of wildlife. These emergent effects, they were not planned. In fact, if you watch that video that I avoided studiously, some of the scientists that introduced these wolves were shocked, their word, by some of the effects. This is the underlying complexity at play. Who remembers the Arab Spring? In this room, I assume everybody, right? That's the gentleman pictured here, Tarek El Tayeb Mohammed Bouazizi. In December of 2010, out of frustration and anger with the municipal authorities who had confiscated his goods and wouldn't allow him to pursue his livelihood, suffered tremendous humiliation and set himself on fire. So that act, that single act of defiance, frustration, anger, rage, led to multiple demonstrations and protests throughout the country, toppling Ben Ali, who had been president for 23 years, and cascading effects throughout the region, right? The fall of Gaddafi, the fall of Mubarak. What do these two cases have in common? So totally disparate on the face of it, when you dig down deeper, it's complexity. We define complexity by the amount of information that's in the system, but that's a more technical definition. We can think of it as many moving parts, feedback loops, nonlinear effects, emergent properties. Because of this structure, cause and effect is really hard to see, hard to understand, and very hard to manipulate, which is why you get these emergent properties and these surprises when you do some of these experiments. But there's also good news. And that is, if we get the mechanisms right, we can model many, many different types of systems, from subatomic to economic, which is amazing. The key is to see the parts and the whole, the feedback loops and the systemic effects at the same time. So our question, what effect does the decision to deploy resources in a complex strategic landscape have on the resilience of that system? So that's our basic fundamental research question, right? So we have a decision-making model, but the minute we start engaging decision-making, we realize it means something different in business than it does in foreign policy analysis, than it does in strategic studies. Likewise, resources. If you ask a banker versus a general, you're going to get different answers. And we found that resilience is really difficult to measure in different domains. This is complexity. So one of the things it forced us to do is to look at these different theories from these different disciplines and try as much as possible, whenever possible, to reconcile them. And what you see here is a map of a complex adaptive system basically designed by John Holland many years ago, but infused with phenomenological concepts coming from Hannah Arendt and Alfred Schutz. So the basic science of complexity coupled with phenomenology, and Schutz was a sociologist, by the way, and Arendt a political theorist, right? So now we've coupled some of these mechanisms that enable us to apply these concepts to the social world. However, in order to make it effective for our purposes, we have to take that deep philosophy and that deep scientific, basic scientific knowledge and turn it into technology. So how can we effectively model resources and decision making, as well as discover the mathematical formulas we can use to measure resilience? So our tool utilizes decision making, spatial analysis, natural language processing, social network analysis, et cetera, et cetera. It is really complexity unto itself. And you'll hear this phrase one more time from me: fight complexity with complexity. And that's what our tool does. Yet, we try to do it in a very clean and simple user interface. So right now, we're working on technology that allows you to enter a simple question in that box, run a neural network based on Google's TensorFlow that returns findings relevant to your question and case study, populates an Excel spreadsheet, and then we run a social network analysis on it, graph theory on it. We are, I would say, about a month away from completing that full cycle. And this is the network world that we speak of. So this is kind of cool, but when you actually see the tool and it's three-dimensional, it's much more interesting because you can move it. Right? So typically when you look at a network like that, you get an impression of what the network is from the image. But when you can manipulate the image, zoom in, zoom out, move it around, some of those initial reactions that you saw to the image change, which is also interesting. But we're doing more here. So if you think about some of these, so basically what we're designing is an influence network tool, because after 15 years of war, we're realizing that we have to battle the information space as much as we're battling the bad guys, right? And so the idea here is that some of these nodes are things like beliefs and symbols, events. And then we have actors and audiences and organizations that have affect toward these things. By tracking the affect toward specific symbols or beliefs, we design influence networks or community detection. By moving the attributes within those nodes, we can now experiment with how these networks adapt to change. So this is the same thing as wondering what would happen when we introduce wolves. As a matter of fact, we have developed technology for the addition and removal of nodes that will reconfigure networks and subnetworks based on the attributes of those nodes and how they link with the rest of the network. So this is really the most direct comparison to the wolf story, right? So if you could think about adding a pack of wolves and what it might do to the landscape, we have developed a tool that actually enables you to experiment with those types of questions. However, another payoff of dealing with complexity is that it sort of has a forcing mechanism. It forces us to go to physics, biology, chemistry, pair these students with political science, sociology, and of course math, computer science, etc. It forces us to work together because there are going to be so many different parts of the system that require different types of knowledges. This is really interesting. We had a team member, Nikita Zemlevsky, who's a physics undergrad, and he thought, how do I, what does my physics do? And I gave him a couple of examples of how principles in physics can then be used, there he is in the bottom, can be used for social studies. And he was amazed by this, right? So this goes to the last question. How do we identify, nurture, recruit, and train and retain top STEM talent to ensure the nation's present and future security? It's a long question, by the way. All right. We ask really complex questions. So we engage them on multiple fronts. We show them how their skills contribute to national security directly. Often this involves bringing in soldiers and putting them in the same room together and getting that conversation going so they know how they're contributing directly. We show them how to connect with other disciplines to create holistic creative thinking. And that is always an exciting experience, particularly when you have military people in the room with the students. All I have to do is sit in the back of the room at that point. The synergy always happens. It's amazing. We also create an environment of care and trust. This is huge. People really do have to feel safe and know that they can offer opinions that may seem wrong or whatever. That's really important. And we let STEM and social science teach each other, grow together, and along the way we try to have a lot of fun. In embracing complexity, we find common problems, sometimes common frustrations, but always common cause. Thank you.